Okay, so welcome everybody again to the AJS seminar of today. Today we have with us Sara Farinelli, that is a third year PhD student under the supervision of Professor Fabio Cavalletti. She will talk about nodal set of Laplace eigenfunction in singular spaces via indeterminacy estimate.
Hi, so this is my first AJS. I don't repeat the title of what I'm talking about because Emanuele read it. So let's start. First, I will do an introduction on the general topic I will speak of. Then I will do an overview of the techniques that we use to solve the problem. And finally, I will go deeper in our work and on the results. So let's see, let's put ourselves in a smooth setting. Given Mg a smooth closed Riemannian manifold, we have that an eigenfunction of the Laplacian operator is a function which satisfies the equation minus Laplacian of f equal to lambda f. The general spectral theory gives us that the spectrum, so the set of eigenvalues of the Laplacian is a sequence converging to plus infinity. Usually with nodal set, we mean the zero set of an eigenfunction. The simplest example to which we can think is of an eigenfunction is sinus, for example, sinus of k of x, which is an eigenvalue in the torus of an eigenfunction of eigenvalue k squared. And concerning with its nodal set, we notice that it's made of 2k zeros. So we can observe that the cardinality of the zero set increases when k goes to plus infinity. So when the eigenvalue goes to plus infinity. This is thanks to the oscillatory behavior of the sinus. What can be said in higher dimension? For example, about this oscillatory behavior of the eigenfunction. For example, in the n-dimensional torus, we have that the sinus of v dot x is an eigenfunction of eigenvalues norm of v squared. So it seems that for norm of v going to plus infinity, the oscillatory behavior is still kept. Another interesting example is the one of the two-dimensional sphere, where eigenfunctions are a restriction of polynomials, in particular homogeneous harmonic polynomials of R3. We see that, okay, in the picture there is the plot of the sign of one of these eigenfunctions in the sphere, and it seems that the oscillatory behavior is still kept, maintained. We can observe from this image that the positive part, for example, the white one, and the negative part of the eigenfunction are mixed together. This is because in smooth Riemannian manifold it has been proved. It has been proved that the zero set, so the nodal set, which is the interface between white part and black part, is C over square root of lambda dense. So in particular, it seems that for lambda going to plus infinity, the nodal set increases topologically. What we ask is if apart from increasing topologically, it increases also its measure. So if it increases for lambda going to plus infinity also is from a measure theoretic point of view. The problem of studying the measure of a zero set of a Laplacian eigenfunction the measure of the zero set of a Laplacian eigenfunction is smooth manifold has been largely studied in the last century. For example, in 1980, Yao conjectured in a paper that for a compact infinity Riemannian manifold, he told that the measure of the zero set is bounded the measure of the zero set of an eigenfunction is bounded from above by a constant times square root of lambda, and from below again by a constant times square root of lambda. So in particular, if the conjecture is true, we can see that the measure of the zero set for lambda going to plus infinity goes like square root of lambda. Many efforts have been done in order to prove this conjecture. In particular, just to do some examples, around the years of the conjecture, there were Bruning and Yao who proved the lower bound for n equal to 2. Then there was an important contribution of Donnelly and Pfefferman who proved the conjecture, but only for real analytic metrics, so for a subclass of infinity Riemannian manifolds. Then, just to mention something, there were Nadirashvili who proved an upper bound, Art and Simon who proved still an upper bound, but for an n, okay, Nadirashvili for n equal to 2 and this for all n. Then there was Kolding and Minikotzi who proved the lower bound, and finally, in 2018, 2 years ago, there was a breakthrough by Logunov who proved, we can say, all the conjectures. So the lower bound and polynomial upper bound for all the infinity Riemannian manifolds. So the conjecture is proved, and we know that the behavior of the zero set of Laplace eigenfunction in the case of Riemannian manifolds. What we are interested in is about what can be said in the context of a general metric measure space. Okay, the fact is that up to now nothing is known in a general metric measure space about nodal set of eigenfunction. I just recall what is a metric measure space. So it is a triple XDM where XD is a complete and separable metric space, and M is a non-negative Borel measure on X, which is finite on bounded sets. The problem, since it is nothing was known, we focused on a particular problem. That was the problem of getting a lower bound to the measure of a nodal set. The fact is that all the tools used in the smooth setting and in the proof in literature are not at disposal up to now because I don't know, they are very smooth tools. So what we needed, it was to attack the problem with a new approach. Fortunately, recently, like 1 year ago or 2 years ago, Steinerberger tackled the smooth problem, but from a very different point of view. That was a point of view we used optimal transport. As we know, optimal transport is like the perfect tool in order to study problems in metric measure spaces. So in order to understand our method, we will say something about optimal transport. We will use in particular L1 optimal transport. In a metric space, L1 optimal transport deals with the problem of transporting a mass, so a distribution of mass into another, minimizing, okay, with the same total mass, minimizing a cost functional which depends only on the distance function. The way to formalize this is the one with the one Wasserstein distance. So we say that given two measures mu1 and mu2, two probability measures, the one Wasserstein distance between them is the integral of the distance function against all the couplings which are probability measures on the product and which satisfy this compatibility condition, where the compatibility is the two marginals being equal to mu1 and mu2. Now we will use the, is there a way to c'è un modo di togliere la righetta nera?
Which one?
Quella con disattiva l'audio, disattiva video partecipanti.
I don't see it. I don't know.
Okay, so
My perspective is fine. So if, yeah, I don't see anything. I don't know.
Okay, so we will use the one optimal transport in a particular situation that I want to make clear so that we can go on fastly. So the situation is the following. We have xdm, a metric measure space, and a function with zero integral mean. We have, in this situation, we have that the positive part of the function f and the negative part have the same total mass. So in particular, they can be seen like two density of mass with the same total mass. So we can transport one into another. We will write W1 F plus M, F minus M, or sometimes F plus F minus, meaning the same. Okay. Now the fact is that we want to get a lower bound of the measure of the nodal set of an eigenfunction. The key ingredient that we used following the approach of Steiner-Berger was an indeterminacy estimate. Let's see which indeterminacy estimate I'm talking of. Again, assumed to be in a smooth setting and assumed to have a continuous function with zero mean with respect to the volume measure of the manifold. The indeterminacy estimate is the following. We have the one cost of transporting F plus into F minus times the measure of the zero set is greater or equal of some ratio depending on the norm of F1 or infinity. How can we read this estimate? We can say that if the cost of transporting F plus into F minus is big, then the measure of the zero set is small. And if the, no, the contrary. If the cost is small, then the measure of the zero set should be big. And vice versa, if the measure of the zero set is small, then the cost should be big. What is the intuition behind this indeterminacy estimate? So what does it mean for F that the cost of transporting F plus into F minus is the same, is small? It means that I can transport most of the mass of F plus into F minus, just moving it by a little. And this is a sign of the fact that the zero set should be big. Let's see these examples. For example, in the first case, we have positive part yellow, negative part white. And we have that the mass, the zero set, which is the interface black, the mass of the yellow, in order to transport the mass in the yellow part to the white part, I should travel like half the side of the square. While in this second case, where we have that the positive part and the negative part are very mixed, and I have a very big interface, so a very big zero set, if I pick a point in the yellow part and I want to reach the white part, I can just make a jump. I can travel just for a small time, small distance. Okay. So this is our indeterminacy estimate. And what we can observe is that in a smooth setting, given an eigenfunction of eigenvalue lambda, then this eigenfunction has zero integral mean. So in particular, we can apply our indeterminacy estimate to our eigenfunction. Now, how can we pass from an indeterminacy estimate to an estimate of the nodal set, which is our target? We have our indeterminacy, so W1 times measure of the zero set. If we are able to give an upper bound of the one cost of F plus into F minus, then we can get a lower bound of the measure of the zero set. Okay, this will be our strategy. In general, there are two ways of giving, in this context, a useful upper bound to the L1 optimal cost, and I will present them in the following. The first way, I called it direct method because it uses direct way because it uses some standard tools of analysis like integration by parts and like the existence of a Kantorovich potential. Just to recall it, we have that a Kantorovich potential for our L1 optimal transport problem. So the problem of transporting F plus into F minus is our Lipschitz function, which allows us to write W1 F plus in F minus like the integral of F times U. So in some sense, the Kantorovich potential gives us a way to write explicitly the one optimal cost. And just to say, Kantorovich potential exists always in very high generality, like hypothesis of fundamental theorem of optimal transport. So let's turn to our way. We wanted to estimate from above the cost of transporting F plus into F minus, where F is an eigenfunction. We write the cost through the Kantorovich potential. We use the fact here. Okay, just a moment. I wanted to show this computation because it's a really two-line computation from which we get the complete bound, and I'm not cheating on nothing. So the first equality followed from the fact that we have a Kantorovich potential. The second one follows using that for F lambda, using the fact that F lambda is an eigenfunction. Then we just integrate by parts. Here we recall that U is one Lipschitz, so we can bound from above is a gradient with 1. And finally, by standard computation, we get that the one cost of F plus into F minus is less or equal of a constant depending on lambda times the norm of F L2. Okay, so in particular, we wanted to have a lower bound on the measure of the zero set. How can we do it? We use the indeterminacy that I showed before. So we have W1 times measure of the zero set greater or equal of norms. Then we bound from above the one cost as I showed before, and we get that the measure of the zero set is greater or equal of norms of F L1, L infinity, L2 times square root of lambda. Okay, this is the first bound that we will try to reproduce in the no-smooth setting. As I said, there are two ways to bound from above the optimal cost. The second way, it's a more sophisticated way. More sophisticated because it uses the heat flow. So we have an eigenfunction and we want to estimate the cost of transporting F plus into F minus. Why we should use the heat flow? The fact is the following. Given a positive function, we have that if we evolve this function with via the heat flow, then thanks to the fact that the heat flow preserves the sign and the total mass, then the evolution of this function will be still a positive function with the same integral mean. So in particular, with the same total mass. So in particular, if we start from F with 0 mean, so F plus and F minus have the same total mass, and from this it follows that also F plus evolved at time t and F minus evolved at time t have still the same total mass. So in some sense it makes sense to compute F plus t, F minus t. Now, another important fact to justify this method is the fact that there is a sort of convergence in W1 distance to the initial datum. The convergence, in which sense? In the sense that if you want to estimate F plus into F minus, then we have that the distance between F plus, the distance between the cost of transporting F plus into F minus is near the distance of to the cost of transporting F plus at time t into F minus at time t, provided that we evolve F plus and F minus of a short amount of time t. So instead of estimating the cost of transporting F plus into F minus, we can estimate the cost of F plus t into F minus t, provided, so of their evolution at time t, provided that we evolve it for a short amount of time. Okay, let's see if evaluating this is useful. We have that thanks to the fact that f is an eigenfunction, then f at time t is equal to e to the minus lambda t times f, provided that lambda is the eigenvalue. So by basic estimates, what we can get is that the distance between the evolution at time t of the positive and negative part is less or equal of e to the minus lambda t. We have a sort of fast decay. Okay, once we get this, we can combine this estimate of the evolution with the estimate of the distance of the cost between the initial data and the evolution, in order to get an upper bound of the cost of the type W1 less or equal of square root of log lambda over lambda times norm, and combining, as we did before, this upper bound with the indeterminacy estimate, we get that the measure of the zero set can be estimated from below by square root of lambda over square root of log lambda times norm of FL1 over norm of FL infinity. Just to notice, in the first way, we add L1 and infinity and L2. Here we have a more, in some sense, clean estimate where appear only L1 and an infinity norm. Okay. Now the strategy is clear. We want to, in some sense, reproduce this procedure of getting a indeterminacy estimate and then upper bounds on the cost in the set of general metric measure spaces. We focus on the subclass of metric measure spaces which satisfy the CDKN condition. So informally, the CDKN condition is a condition which is defined through a convexity of an entropy functional along some geodesics defined via optimal transport. That's why I said that optimal transport is a useful tool for metric measure spaces. For example, CDKN spaces, in CDKN spaces appears transport from the very definition of them. Just to have a general idea, the CDKN condition is a kind of generalized notion for a space of having dimension bounded from above by n and curvature bounded from below by k. Before seeing the precise definition, I want just to recall some standard examples of CDKN spaces. So smooth Riemannian manifold, we reach curvature bounded from below by a constant k, falling in the class of CDKN spaces where n is the dimension. Then measure Gromov-Hausdorff limits or Riemannian manifold of the same dimension and with the uniform bound of the curvature fall again in CDKN class. And finally, Alexandrov spaces of dimension n and curvature bounded from below by k. Just to recall, in Alexandrov spaces, the curvature is a generalization of the sectional curvature. Okay, now we are ready to see the precise definition. So I talked of condition on an entropy functional, which is the following. So given a metric measure space, we have that the entropy of a measure mu with respect to the reference measure m is this integral. And in particular, a space satisfies, metric measure space satisfies the CD0n condition if for every couple of measures, mu0 and mu1, there exists a geodesic connecting them, so a geodesic measure between mu0 and mu1, among which the entropy functional is convex. I decided to show just the definition of CD0n because in this case, when k is equal to 0, the convexity condition is very explicit and is the standard one, while when k is different from 0, we have a more complicated condition where it's harder to see convexity. Okay, an important remark that I want to do is that a special class of CDKN spaces are CDKN spaces in the real line. So what does it happen when we have a space in a space which is an interval in the real line, then the standard modulus, and then the measure which is a weighted measure, weighted Lebesgue measure. The fact is that the CDKN condition translates into a space like this, translates in the sense that this space is a CDKN space if and only if the density H satisfies this differential inequality. So in a space on the real line, the CDKN condition avoids using entropy and transport and translates in a, I don't know, in a differential condition on the density. This fact will be very useful later. So the indeterminacy estimate we proved in CDKN space is the following. Given a CDKN space, we have that given a continuous function with 0 mean, it holds that the cost of transporting f plus m into f minus m times the measure of the zero set. Yeah, we can say the measure of the zero set is greater or equal of a constant depending on the space times a quotient depending on the norms of f as before. Let's make some remark on these results. The first remark is that in the previous estimate, in the previous indeterminacy estimate, we saw that there was the Hausdorff n-1 dimensional measure. Here we see the perimeter. Okay, first we say that in the context of general metric measure spaces, is it possible to give a definition of perimeter starting from BV function as in the smooth case? So are well-defined sets of finite perimeter, and the fact is that it is not known a theory like the Giorgi theory, which links the perimeter and the Hausdorff measure. So we needed to use the perimeter that seems to be the right n-1 analog in singular spaces of the Hausdorff measure. And we can say that in the smooth case, we recover the Hausdorff measure. Another important remark that I want to do is that, okay, I separated this quotient from norm of FL1, and there is a reason. As I said, we followed an approach of Sajiv and Steinerberger. They proved in the smooth setting the indeterminacy estimate, in particular in the unit cube, but their estimate appeared with the exponent 4 minus 1 over n. The fact is that Steinerberger conjectured that the estimate should hold with exponent 1. Later, like last year, Carol Massanet and Ortega Cerda improved on estimate of Steinerberger, proving extending it from the unique cube to smooth compact Riemannian manifold, and they proved the estimate with exponent 2 minus 1 over n. Okay, just notice that the smaller the exponent is, the better is the estimate, because here we have L infinity bigger than L1. So a byproduct. Another thing is that the fact that Carol Massanet and Ortega-Cerda proved that the exponent of this quotient cannot be decreased under 1. So also they believe that 1 is the right exponent, and the byproduct of our theorem is that the answer to the question in some sense is yes, the estimate holds with the exponent 1.
Sorry, Sara. The capital D is a bound on the diameter.
Yeah, it is a bound on the bound on the diameter. Here I put k minus, meaning that okay, for k positive we don't need the bind. We have the bound on the diameter for free by the CDKN condition, but here it doesn't appear. So for k positive, here we have 0, and the constant became 1. While for k less than 0, we need a bound on the diameter, which appears here.
Okay, thank you.
Sorry, I didn't write. Okay. How did we manage to prove this estimate?
Is M is a probability measure, or is no? It's finite unbounded set. Or...
M is a general measure.
Okay.
Okay, so how did we manage to prove the estimate? We used a standard strategy. We used a standard strategy that is used in the set of CDKN spaces. That is the strategy of reducing our problem to a problem in the real line. Once that we reduce ourselves to the real line, we can get the estimate in the real line, and managing things in the real line is always better than in abstract spaces. Then, for who knows this integration, we get the estimate in the real line, and we reintegrated it in order to get a whole estimate in the whole space. So I will focus only in these two steps because from my point of view, they are more interesting. The first step is the step of reduction to one-dimensional case. So we will go through the theorem using the image. We try to go through the theorem using the image. The reduction to one dimension uses the localization technique. What does localization say? So starting from a CDKN space, assume to have a function with 0 mean, then we can partition the whole space X into spaces X alpha, which are geodesics. And in some sense, together with the partition, we get a disintegration of the measure M into measure M alpha, which are measures on this X alpha. So we start from a space, we partition it into geodesics, and we slice the measure M into measure M alpha. Okay, the property of these subspaces is the two more important properties are the following. The first one is that starting from a function with 0 mean, along the spaces X alpha, f preserves the fact of having 0 mean. So the integral of f in X alpha with respect to the measure M alpha is still 0. And the second important fact is that this geodesics X alpha, together with the measure M alpha, verifies still the same CDKN condition. Okay, another important fact is that each of these spaces X alpha, DM alpha, being a geodesics, is isomorphic to a CDKN space in the interval. So at the end, we can try to prove the estimate in a space in the real line. Let's see just the idea. First, we need a base case where we are in 0, 1 with modulus and the Lebesgue measure. So we assume the weight of the measure to be constantly 1. We have a continuous function with 0 mean, and we assume, so that's why I call base case, we assume f to have only one change of sign in the point x bar. How does the indeterminacy estimates reads? We want W1 f plus f minus times measure of the zero set, that in this case it is 1 point, so the zero-dimensional measure is the counting measure, so we want W1 times 1 greater or equal of something. Let's try to estimate from below the one cost. We have f plus, we have f minus, we want to transport f plus into f minus. We observe that the more the mass is near x bar, the less the cost will be. So in particular, we can take the mass of f plus and push it towards the point x bar, push, 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 and we diminish the cost. Okay. Yeah, when we push the mass, I mean pushing, maintaining the same total mass. The fact is that if we push everything towards x bar from the part of f plus and from the part of f minus, at the limit, the density will start to increase, and at the limit, everything will be concentrated in x bar. So the cost will be 0. So I need to, in some sense, put a constraint to this pushing procedure, and the constraint that I put is that I decide to not allow to the density to overpass the norm of FL infinity plus and the norm of FL infinity minus. So I push, but I do not allow to my mass, to my density, to overpass these red lines. What I get at the end in this, with this procedure that, as I said, decreases the cost, is that I have two-step function, which I can compute explicitly with the same mass of f plus and f minus, and with dates f plus L infinity and f minus L infinity. The cost of transporting key plus into key minus can be computed explicitly, and the bound that I get is W1 f plus f minus greater or equal of this term. Just keep in mind this term because we will use it now. Okay, so the term is a norm of FL1 over minimum on norm of f plus f minus L infinity. As I said, we wanted to prove the case, the estimate along the geodesics, which are weighted intervals. So assume to be in a weighted interval with a CDKN density. Again, we have a continuous function having 0 mean, this time with respect to the measure h dx. And we again put us in a base case in which f has only one change of sign. What can we say? The first observation is that h is a positive density, so in particular f times h change signs as the same sign of f, and f times h is still a function with zero mean. So we take what we proved in the previous slide and we apply it to the function f times h. What we get is that the cost of transporting f plus h into f minus h is greater or equal of this term. Okay, our target is to prove the indeterminacy estimate. So here we would like to have the perimeter of the zero set. What is the perimeter of the zero set? What is the perimeter of the set where f is positive? F is positive in 0 x bar. what is the perimeter of this set with respect to the measure HL1. So as in the case of only Lebesgue measure, we have the delta function at the boundary of the set. Here we have a weighted delta function, so the perimeter is exactly h of x bar. So in some sense, we would like here h of x bar that we could extract from this minimum. It is possible to extract it from this minimum. The answer is yes, and that here is the point where the fact that H is a CDKN density plays its role. So in particular, a CDKN density has log concavity properties, and thanks to these log concavity properties, we are able to estimate the minimum of these two L-infinity norms with H at the point x bar times the norm of F L-infinity. And we got the estimate in the weighted interval in the case of 1, 0. Yeah, the case passing from the case of 1, 0 to many zeros is not so interesting, and it's in some way direct, so I won't skip it. And the same is for reintegration. I think that the key point is proving the estimate in this case. Okay, now let's go to the main part of the results, that are the estimate for the nodal set. Yeah, I talked of nodal sets and eigenfunction in metric measure spaces, but what is a Laplacian in this context? We have a notion of Laplacian which is available, and in some sense is defined via integration by parts. So given a function f, we say that a measure mu is a Laplacian for f if it is satisfied an integration by parts formula against g test function. So we have g times Laplacian of f is greater or equal of this term, where this term is a metric analog of gradient of f, gradient of g, in our context where we don't have gradients. Okay. At this level of generality, the Laplacian is not so good. So in particular, it is not unique and not linear. We can define eigenfunction. We have that f is an eigenfunction if lambda f times m is a measure which is a Laplacian for f lambda. And fortunately, it turns out that eigenfunction have zero mean, but the spectral theory does not hold in this context, or I don't know if it holds. In particular, eigenfunctions are not orthogonal, and we don't know if the set of eigenvalues is discrete. So at this level of generality, we got the following estimate using the first method, which used integration by parts that I showed before. Given an eigenfunction, we have that measure of the zero set, the measure of the perimeter of the set where f is positive is greater or equal of square root of lambda, that is good because recalls the Yau conjecture, times this bad term involving the norms of f. Okay, so as I said, the context of CDKN spaces is not so good for the Laplacian because we have like too much generality. So we restricted also to the subclass of spaces called RCD spaces. Well, RCD, as you know, stays for Riemannian. Yeah, just to mention, an RCD space is a space where which satisfies the CDKN condition, and in addition, the Banach space W12 is also Hilbert. So we have a scalar product. This Riemannian structure gives additional information on the Laplacian and a better behavior of it. So in particular, we have that it is this time a single valued linear operator. And that, as in the standard case, spectral theory hold. Eigenfunctions are still a base of L2. And an important property that I want to mention is that we have a linear flow, and that the convergence to the initial datums is proved, so that we could apply the second method in order to getting our lower bound. And what we got is the following. So given an RCD setting, RCD space with k is greater or equal than 0, the perimeter of the set where f is positive is greater or equal, this time, is greater or equal of lambda to this power over square root of lambda. Well, the positive thing is that we were able to get rid of the bad term involving the norms. The negative thing is that for lambda going to plus infinity, these terms goes to 0. Okay, I think that's all. Thank you.
Thank you, Sara, for your seminar. Now it's the moment for question. If anybody has a question, you can ask directly. Or she.
Can I ask a question?
Yeah.
Hi, Sara. I was just wondering if there's any particular reason the Wasserstein distance you're considering is the one Wasserstein distance, and if the indeterminacy estimate holds for other Wasserstein distances, at least in the smooth case.
I think that the method we use to get this particular estimate holds are only for the exponent of the distance equal to 1.
Mm-hmm. Okay. Thank you.
Okay, so it seems to me that there are no more questions. So I propose to thank again Sara for the seminar, and we meet as usual on next Friday. Thank you all. Bye.
Bye.